Okay, so the next thing that we have here is example number 18, and about what we had in the previous video. There is, as I was looking at the examples, there is actually going to be, I think in this video itself is going to be a couple of examples where we will learn the meaning of basically the identity, the meaning of identity functions on set A and B and so on and so forth. So we do not really need to worry about all of those things. Now, example number 18, we have shown that if you want to show that if basically if f is a function from A to B, if f is a function from A to B and g is a function from B to C, R1 1, R1 1, then G O F from A to C, then G O F from A to C is also 1 1. Okay. Now the reasoning that you can use here is that we are saying that f from A to B and g from B to C are 1 1, meaning that if I assume that I have some set A here, and if I assume that I have some set B here, and if I assume that I have some set C here, and f is a function from A to B, that means that you can imagine that f is a function from A to B, and g is a function from B to C. So this is going to be g, right? G is a function from B to C, and these functions are 1 1, meaning that for example, if I have the set A and if I have the set B over here, and if I have 3 elements here, 3 elements here, then the function is going to be 1 1 if every distinct element of A has distinct basically images in the set B. In that case, you could say that f is 1 1. And of course, the condition that we used for this was that we said that for every A1, A2 belonging to the domain of the function, then if f of A1 is equal to f of A2, that implies that A1 is equal to A2, meaning that you're talking about the same A1 and A2s basically. So that's basically the meaning of 1 1. Now the question here is that basically we want to show that f basically from A to B and g from B to C are 1 1, and so then g O f from A to C, g O f is basically g O f is the same. G O f of x, for example, is equal to g of f of x. G of f of x is equal to g of f of x, right? So g of f of x is equal to g O f of x is equal to g of f of x, which means that which means that basically the argument of the function g becomes the output of the function f of x, meaning that again, in the same example, if you have a and if you have b over here, or b and c over here, then f goes from a to b, and g goes from b to c. And now if you have an x over here, f, and give it to x, it will give you f of x. And if you give f of x to g as an argument, it will give you basically g of f of x, which is denoted by g o f of x. Now, this g o f of x is the composition of f of x and g of x, and it's a function that maps basically the elements from A directly to the set C, meaning that this would be g o f of x, right? Now, we want to show that basically if f and g are 1 1, then g o f is also 1 1, right? Now, in order to do that, what we need to do is basically so let's suppose that, for example, since basically since f and g are 1 1, you can say that basically g of f of x1 is equal to g of f of x2. Now, in order to show that the function is 1 1, and here we want to show that basically the function g o f is 1 1. So in order to show that the function is 1 1, we said that for every, for example, a1 and a2 belonging to the domain, if f of a1 is equal to f of a2, if that implies that a1 is equal to a2, then that means that basically f is a 1 1 function, right? So you can make this assumption that for the function that you want to show that the function is 1 1, that this is the case. If you can prove that basically that your assumption implies this conclusion, then that means that that function is 1 1. So I can say that suppose that for this function g o f, basically g o f of some, for example, x1, some g o f of some, for example, some x1 is equal to g o f of some x2, for example, two distinct x's, for example. And what that means is that g o f, as we argued before, is basically g of f of x1, right? And g o f of x2 is equal to g of f of x2. And well, since g is 1 1, we said here that g is 1 1. So we know that g is 1 1 if f of a1 is equal to f of a2, that implies that a1 is equal to a2. And since we know that g is actually 1 1, then I can say that f of x1 is equal to f of x2, because this is the argument of g, and so since I know that g is 1 1, then I can then that implies this one. Now also f is 1 1, so if f of x1 is equal to f of x2, that implies that x1 is equal to x2. So we have assumed that GOF of x1 is equal to GOF of x2, and then we have concluded that x1 is equal to x2. That means that GOF is basically 1 1 or injective right? So that is, and what that means is that and these are important to understand. What that means is that basically if you have some f from a to b, you have some set a, you have some set b, you have some set c, and f goes from a to b and g goes from b to c. If f is 1 1 and if g is 1 1, then FOG is going to be 1 1. So this is injective and this is also injective, so then this is going to be also injective. That's basically what you learn from this exercise, meaning that in each of these exercises there is actually a point that needs to be learned so that it can be used in the rest of the text. Okay. Let's see. Okay, so now the next example number 19 is the exact same situation, except that f and g are, instead of 1 1, are unto, meaning that you want to show that if f is a function from a to b and g is a function from b to c, if these two functions are unto, then GOF from A to C is also unto. Right? So the solution is, so basically unto means that basically f is surjective, g is also surjective, meaning that if I assume that, for example, there is some set A here and there is some set B here and there is some set C here, and if f goes from A to B and if g goes from B to C, then and f and g are both unto. So if I assume that f is unto and g is also unto, so what that means is that every element of B is the image of some element of A, meaning that there is no element left in B which is not an image of some element in A. And the same is true of basically every element in C in relation to every element in B, meaning that every element in C will be the image of the image of some element in B because G is on 2. So then you can use the same argument. Of course, I gave you the argument in the reverse order, meaning that you have to use the inverse or basically the reverse order of the argument that I gave you, meaning that you need to start from C and then you will get to A. Now, in order to do that, you can say that basically given an arbitrary element Z, you can say that given an arbitrary element Z belonging to C, there exists a pre-image Y. There exists a pre-image, and you already know what the pre-image is. Basically, if I have two sets here, A and B, and there is a function on these two sets, meaning that there is an f going from A to B. Now, suppose that the rule of the function is that, for example, A1, A2, and A3, and B1, B2, and B3, then if A is connected to B, if A1 is connected to B1, A2 is mapped to B2, and A3 is mapped to B3, then in this situation you can say that A1 is the pre-image of B1 under F. You can say that A1 is the pre-image of B1 under F, and you can also say that B1 is the image of A1 under F. So you have the pre-image and you have the image, right? So now that we understand what the word pre-image means, or what basically the word pre-image means. So we said that basically given an arbitrary element Z belonging to C, there exists a pre-image Y of Z under G such that basically there exists a pre-image Y of Z under G such that G of Y is equal to Z. Since G is onto. And further you can say that for Y belonging to B, for Y belonging to B, there exists an element X in A. There exists an element in A with f of X. There exists an element X in A with f of X is equal to Y, since f is onto. since f is onto, right? Therefore you can say that g of f of x, or g o f of x, or which is equal to g of f of x, is equal to g of y. You can see that basically f of x is equal to y, so g of y, and g of y is equal to z, which is equal to z, because g of y over here is equal to z, showing that basically that g o f is onto. So far what we have learned is that if we have basically a set A, a set B, a set C, if f goes from A to B, and if g goes from B to C, so what we have learned is that if f is a function from A to B, and if g is a function from B to C, if f and g are 1 1, then g o f is also 1 1. Moreover, what we have also learned here is that if f is a function from A to B, and g is a function from B to C, if f and g are basically onto, then g o f is also onto. So that was question number 18 and 19. Okay.